Hello, welcome to this new lecture of the course Transportation Network Analysis. So, in the last class, we were discussing about discrete choice models, and we had just started to discuss about multinomial logit model. So, we will continue the discussion here. So, we had mentioned that the error terms in the multinomial logit models are independently and identically distributed Gumbel variates. Okay. So, we had looked at the cumulative distribution function of Gumbel variables in the last lecture, and we had also seen that since that distribution is already defined, we can also calculate the probability of choosing different alternatives from the definition of these probabilities of choosing different alternatives, that it should be equal to the probability that the utility of the first alternative is greater than or equal to the utility of all the other alternatives and so on, right. So, we will be skipping the derivation of using the distribution of those error terms to obtain the probabilities of choosing different alternatives, because that is slightly complex in the case of logit model, and we will be directly mentioning what expression finally comes out. So, the choice probability pk, that is the probability of choosing the kth alternative in the logit model, is given by this expression. Okay. So, here Vk is the systematic component or the measured utility of the kth alternative, and here in the denominator we are summing this e to the power Vl, where we are going through all the alternatives that are present. Now, here we have omitted this parameter a, which was taking into account various attributes and the characteristics of the decision maker from pk and vk here. So, I mean, ideally we should have written pka here, but and also similarly for vka here and so on, but we are not doing that, so that there is simpler expression here, but we kind of know that it is actually present even though it is not mentioned here. Okay. So, alternatively, this expression for choice probability of the kth alternative can be described as follows if we divide by e to the power vk on top and bottom on the right hand side. So, if we do that, then this is the expression for the choice probability of the kth alternative that we get. Okay. So, this is what we get, 1 divided by 1 plus the summation for L not equal to k e to the power Vl minus Vk. Okay. So, we will see why we are doing this, because this kind of expression is useful when there are only two alternatives. So, in the case of binary logit model, that is when there are only two alternatives, this model can be written as follows. So, the probability of choosing the first alternative is this, okay, and if we divide by e to the power v1 on both the numerator and the denominator, this is what we get here. Okay. And similarly, the probability of choosing the second alternative is 1 minus of p1 here. Okay. And this can be written in this form, 1 divided by 1 plus e to the power v1 minus v2. Okay. So, what is important here is that when we are writing this, that p1 is equal to e to the power v1 divided by e to the power v1 plus e to the power v2, and then we have this e to the power v2 minus v1 here. So, we see that the probability of choosing the first alternative is actually only dependent upon this difference of v2 minus v1, okay, nothing else. So, depending upon what is the difference v2 minus v1 here, it will be determining the probability of choosing the first alternative. Okay. So, this is interesting, but the same we cannot say if there are more than two alternatives, okay, because then there will be other terms also which will be having this exponential powers. So, let us take an example here. Suppose there are two routes and the utilities of the two routes are specified as follows. So, the utility of the first route is given as this, u1 is equal to v1 plus this error term, where v1 is equal to minus 2t, where t is the travel time of route 1. Okay. Okay, now t is actually the measured travel time of this route 1, and suppose utility of the second alternative is given by V2 plus the error term of the second alternative, where V2 is a function of t dash and is equal to 1 minus 2 t dash, where t dash is the travel time of route 2. Okay. Now, one more thing to mention here is that even these two error terms that are present for both of these two alternatives, they are IID Gumbel variates. Okay, so they are independent, first of all, that is the important thing, the first I, and they are identically distributed as given by the Gumbel distribution. Okay. So, that is why although I am not specifically saying here what is the distribution of these two error terms here, but since we are discussing about Logit model, so it is kind of implicit that these error terms will be IID Gumbel variates. Both of them will be independent of each other and they will have identical distribution as given from Gumbel distribution. Okay. So, therefore, the probability of choosing part 2 is given as follows. It is 1 divided by 1 plus e to the power minus 1 minus 2 times t minus t dash. Okay. So, we have divided by this e to the power v2 on the numerator and the denominator, and this is what we get here. So, you can see here that the probability of choosing the second alternative is actually only the function of t minus t dash, everything else is a constant here. Okay. So, therefore, if we plot the probability of choosing the second alternative versus t minus t dash, so this is what we will be getting. So, here you can see that on the x axis we have t minus t dash plotted, and this is the probability of choosing the second alternative P2 here plotted on the y axis. Okay. So, what you can see here is that as t minus t dash is increasing, P2 is also increasing, which is also expected from this expression, because there is a minus sign here. Okay. So, if t minus t dash increases, the quantity in the denominator decreases, but this overall quantity will increase. Okay. And physically also it makes sense, because if t minus t dash is increasing, so what it means is that the travel time on part 2 is becoming lesser and lesser as compared to the travel time on the first path, and therefore the fraction of travelers who should choose part 2 should increase as t minus t dash increases. Okay. So, t is the travel time that is experienced on the first route and t dash is the travel time on the second route. Okay. So, if t minus t dash is increasing, so it means that the travel time on part 2 is now lesser and lesser as compared to the travel time on path 1. So, effectively more travelers should choose part 2 as compared to path 1. However, you should remember that the attractiveness of these two paths is actually given by these utilities u1 and u2. Okay. And these are random quantities. Okay. So, the choices of these two paths is not just a function of the travel time exactly, because travel time, although is a attribute that is coming into account while we are describing these utilities u1 and u2, but there are also error terms that are present in u1 and u2, and that is why that makes u1 and u2 as random variables or stochastic variables. Okay. And therefore, there is some probability of choosing alternative 1 and some probability of choosing alternative 2. Okay. Okay. So, with this, for now we end the discussion on the multinomial Logit model, and now we will be moving towards multinomial Probit model. Okay. So, this is the second discrete choice model that we will be focusing in this lecture. So, in the Probit model, it is assumed that the random error term for each utility is normally distributed. Okay. So, before this, in the Logit model, we were assuming that the random term of each utility is IID and Gummel distributed, okay, but now it is changing here. So, we are assuming normal distribution for the error term here, and therefore, the joint density of the error terms is a multivariate normal distribution function, which is in short referred to as MVN here, okay. Now, you must have all seen how does a normal distribution function looks like. So, it is a bell shaped curve like this, okay. So, its range is from minus infinity to infinity. Now, this is the case when there is a single variable, okay. Now, here since there can be multiple alternatives that are present and there will be an error term associated with each alternative. So, we are here focusing on a multivariate normal distribution function, okay, which will be giving the joint density of all of these error terms in different alternatives, okay. So, for example, if it is the case of two alternatives, so we will be having two error terms. So, then these two error terms will be given by the distribution of bivariate normal distribution function, okay. So, how does that look like? So, suppose if you have a bell, okay, a two dimensional bell, and if you are looking at the top, okay. So, then suppose the z axis which is coming out is actually representing the values of the probability density function, and the two axes x1 and x2 are denoting the error terms that you have, okay. So, this bivariate normal distribution function will be looking like a two dimensional bell, okay, which is kind of coming out, okay. You can think of it as a three dimensional bell also, where the third dimension is representing the probability density function at any given point x1 and x2, okay. In this case, x1 will be the value of the first error term and x2 will be the value of the second error term. So, this MVN distribution is the multinomial extension of the well known normal density function, okay. So, this error vector has k components because there are k alternatives here, and therefore, since it is given by this multivariate normal distribution function, it has a mean vector bold mu that has k components, and there is a k cross k covariance matrix here, okay. So, this notation that the error term is given by a multivariate normal distribution function is denoted by this here, okay. So, we have this vector which is denoting the mean vector, and this is the covariance matrix, okay. Now, since we have mentioned that in discrete choice models we assume that the expected value of each error term is equal to 0 in every alternative. So, therefore, this mean vector has to be identically equal to the 0 vector, okay. So, what it means is that suppose if there are only two alternatives, so then if suppose we plot this distribution of bivariate normal distribution of the two error terms, then what you will be seeing is that the origin of this graph 0 comma 0 will denote the mean of this joint distribution of two variables that we have here, okay. And also just remember that when there was single variable in the normal case, we used to represent by this notation, right, n mu sigma square. So, this kind of notation is an extension of this here, okay, when we have more than one variables which are given by this multivariate normal distribution, okay. Okay. Now, remember that the systematic component of this utility is a deterministic component, okay. So, therefore, the expected value of the utility vector is equal to the systematic component or the deterministic component V here. Okay. So, this is what we had seen for the case when we were discussing about the theory of um, discrete choice model. So, if you take the expected value of the utility, so since the expected value of the error term is 0, so it is equal to the expected value of the systematic or the deterministic component, which is this, and since this is a deterministic component, the expected value of this component is the same as this VA here. Okay. Now, suppose if you have to determine the covariance of this utility function. Okay. So, then since this first component VA or the systematic component is deterministic, so the covariance associated with that is 0. So, whatever covariance is there for UA is given by this covariance matrix of the error term. Okay. So, what we can write in short is that this utility vector is a multivariate normal distribution where the mean is given by the systematic component or the deterministic component, and the covariance matrix is equal to the covariance matrix of the error term. Okay. So, again to summarize, since the systematic component or the deterministic component does not have any variance, so therefore, when we are suppose trying to determine the expected value of this utility function, now we also know that the expected value of the error term is 0. So, therefore, this expected value is just equal to the expected value of the systematic component, and that is equal to just VA, whereas when you are determining the covariance of this utility function here, then since the first component, the systematic one, does not have any covariance, so it will just be equal to the covariance of the error term. Okay. Okay. So, let us now consider the binary case here. Suppose we have two utilities U1 and U2, where U1 is equal to V1 plus the error term of the first alternative, and U2 is equal to V2 plus the error term of the second alternative. Okay. So, then the distribution of the error term is given by this here, that is, it is a multivariate normal distribution, and in this case bivariate normal distribution, where the mean vector is 0, and since there are only two variables here, so it is actually identical equal to 0, 0, and the covariance matrix is equal to the covariance matrix of the error term. Okay. So, suppose these two error terms of the two alternatives are having this as the covariance matrix. Okay. Okay. So, now if you have to determine the probability of choosing the first alternative, so then it is equal to the probability that the utility of the first alternative is greater than or equal to the utility of the second alternative. Okay. Utility of the first alternative is the systematic component of the first alternative plus the error term of the first component, and similarly we can replace the utility of the second component also here, or the second alternative here. So, we can take the error terms on one side. So, this is what we get here. Okay. Now, since E2 and E1 are given bivariate normal distribution, so from the properties of these distribution, it is known that the combinations of such error terms, such as the differences here, is also another normal distribution function. So, this E2 minus E1 is a normally distributed random variable that has mean 0 and variance sigma square, where sigma square is sigma 1 square plus sigma 2 square minus 2 sigma 1 2. Okay. So, these are some standard concepts here. So, if you do not recall these concepts, I will suggest you that you pick any standard book on probability and statistics, and there you revise the topics on expected values, covariance, and so on. So, there when you will be seeing the discussion related to normal variables. So, this is the property of the normal variables, that if you have these two error terms E1 and E2 which are given by a bivariate normal distribution. So, E2 minus E1 will be again another normal distribution function that has 0 mean and variance is given by this here, okay, where the sigma 1 square, sigma 2 square, sigma 1 2 and so on, these were the components of the covariance matrix of the error term, okay. So, if this is finally another normal variable, so therefore, we can then use the standard normal tables that are available that provide the cumulative distribution function values, okay, because if you recall that the cumulative distribution of normal distribution function is not a closed form expression. So, usually if you have to take the cumulative distribution function values for a normal distribution, so we usually refer to some standard charts or tables that are there, okay, because there is no closed form expression for determining the CDF. What does a closed form expression mean? That it cannot be written down in form of the known functions that we have, okay. And how did those charts got developed where we have these values of cumulative distribution function known? Because they were obtained using some numerical integration and so on, okay. So, what this means here is that we have to determine that the probability that this new quantity E2 minus E1, suppose let us represent it by this E3, this is less than or equal to V1 minus V2, okay. So, if suppose V1 minus V2 lies here, okay, so we have to determine, so this is E3, as we have argued, is another normal distribution variable, okay, that has 0 mean and variance given by this, okay. So, if this is suppose the normal distribution function of this E3, so we have to determine what is the probability that this variable is less than or equal to V1 minus V2. So, that means that we have to find value of this integral here, okay, and that is what is provided from the standard charts that are available for normal distributions, okay. So, therefore, this probability of choosing the first alternative is equal to phi of V2 minus V1 divided by square root of sigma square, okay, where phi is the cumulative distribution function of standard normal distribution, okay. So, once these, note that these V1, V2 values are given to you because these are deterministic values. So, we will be aware about that, these will be inputs and sigma will also be given, okay. So, once these are given, we can determine the value of choosing the first alternative by looking at any standard normal distribution table. So, since we know all of these three values here, so we will be knowing what is the value in this bracket V2 minus V1 divided by sigma, okay. So, whatever that comes out, I mean suppose that is 0.2. So, then we will have to determine phi of 0.2, okay. So, then we go back to any, so this is what, this is the probability that this error term which is this E2 minus E1. So, that always takes value less than or equal to 0.2. So, for that we can refer to any table, standard table for determining the value of this, okay, for normal distribution functions. And why we are doing that? Because this phi or the cumulative distribution function of standard normal distribution is not a closed form expression, as I mentioned. But this was for the case when there were only two alternatives, okay. This computing the choice probability becomes even more complex when there are more than two alternatives, okay. So, then it is not very straightforward case of determining what is the probability of choosing one alternative and so on, okay. And why is that? Because when there are two alternatives, so then what we will have to write is that the probability of choosing the first alternative is equal to PR. Now, this U1 is greater than equal to UL. Now, this helps to hold for all L not equal to 1, okay. So, suppose if there are three alternatives, so we have to calculate that probability that U1 is greater than equal to U2 and u1 is also greater than or equal to u3. So, because of this additional term that is coming, determining this overall probability is not that easy, because when there are only two alternatives, you have to just determine probability of u1 being greater than or equal to u2. But now there are additional things that also we need to determine. Okay. So, the choice probability for the cases with more than two alternatives need to be estimated either through an analytical approximation or a Monte Carlo simulation. Okay. So, these analytical expressions usually become computationally burdensome when the number of alternatives increase. So, for most practical purposes, this Monte Carlo simulation is the best approach. So, we will be discussing that only here. Again, the reference for all of that can be referred to this book by Joseph Sheffy on urban transportation networks. So, suppose that we have to determine what are the probabilities of choosing these different alternatives, and suppose we have more than two alternatives. Okay. Now, what we know is that we have these values of the systematic utilities. Okay, these measured or the deterministic components of these k alternatives, these are already known, v1, v2 till vk. Okay. What other thing that we know is that we also have the distribution of the error terms given to us. So, if there are k alternatives here, so we will be having this multivariate normal distribution function whose parameters will be known. For example, one thing is sure that the whole mean is lying at the 0, so it is 0 vector, and the error terms will be given by some covariance matrix. So, that covariance matrix will be known to us. Okay. So, given that we have these exact values of the systematic utilities and we have the knowledge of the distribution of the error terms, what we can do is that in this Monte Carlo simulation, we will be doing a fixed number of iterations. So, in every iteration, suppose we are at the nth iteration, we will be drawing a sample of the values of these error terms from this multivariate normal distribution. So, what does that mean is that we have this multivariate normal distribution given to us. Okay. So, we will randomly pick any one point from this multivariate normal distribution. So, that one point actually will be a vector that will be having the value of the first error term, the value of the second error term, until the last error term for the kth alternative. Okay. And then we can calculate the perceived utility of each alternative, that is uk at this nth iteration as vk, which is already given, and this is the error term for the kth alternative at this iteration, which we just computed from this sampling process. Okay. So, we have now ukn for each alternative here. So, now what we can do here is that, see, if we are suppose at the first iteration, so we got some random values of the error term of the first alternative till the kth alternative, and we added that to get what is the utility of the first alternative, utility of the second alternative till the utility of the kth alternative. Okay. And now we determine which alternative has the highest utility. Okay. So, we do this comparison. Okay. So, suppose whichever alternative has the highest utility, we record that. Okay. So, this is one iteration of the Monte Carlo simulation we have done. Suppose we do a total of n times here. Okay. So, then every time we will be sampling the values of the error terms from this multivariate normal distribution, and every time we will be computing these values of the perceived utility of each alternative, and we will be determining which alternative has the highest utility. Okay. So, for example, if we sample this 1000 times in this Monte Carlo simulation, it can happen that maybe 100 times the first alternative is getting the highest utility, maybe 200 times the third alternative is getting the highest utility, maybe 150 times the sixth alternative is getting the highest utility, and so on. So, we keep track of all of that. Okay. So, let nk be the number of times each alternative k is recorded. Okay. So, that means that nk is the number of times each alternative k got the highest utility. So, then the choice probability of the kth alternative is given by nk by n. that is the number of times that alternative had the highest probability divided by the total number of iterations of this Monte Carlo simulation. Okay. And in the limit that this n goes to infinity, that we are doing a lot of iterations, that is this n is sufficiently large, this probability of choosing the kth alternative will be going towards this limit nk by n. Okay. Okay. So, with this we have kind of ended the discussion on the multinomial Probit model. So, in the next class we will be starting the discussion on another concept called satisfaction function. So, with this we end here today. Thank you.